Hello and welcome back to the channel. Today we are going to discuss the topic orthogonal projections. So orthogonal projections play a crucial role in various applications like dimensionality reduction, regression analysis, and optimization in machine learning and AI. So in this video we will break down the concepts from the basics to its real-world applications. So firstly, what is orthogonal projection? So an orthogonal projection of vector B onto a subspace is its shadow onto that subspace when a perpendicular or the orthogonal line is drawn from B to the subspace. So for better understanding, we can just have a look at this, that consider a plane and a light source shining directly above the object. The object's shadow on the plane is the orthogonal projection of the object onto the plane. Mathematically, we can define orthogonal projections as given a vector B and a subspace V, the orthogonal projection of B onto V is the vector P in V that is closest to B. This seems confusing, but when you will read it out for 2 to 3 times, you will understand what actually the statement is trying to say. So mathematically, the projection P satisfies this equation. Now, moving on to orthogonal projection of a vector onto another vector. Let's say we are given a vector B and a non-zero vector A. The projection of B onto A is given by B dot A divided by A dot A and A, where B dot A you can understand is the dot product of the vectors and A dot A is the magnitude squared of A. Now let us understand it using an example projection onto a vector. Let's say we are having two vectors B and A with the following components. The first step is to calculate the dot product of B and A. When you calculate it, you get the answer as 10. The next step is to calculate the magnitude squared of A vector, that is A dot A, and the answer for this will be 5. The last step is to compute the projection. This is nothing else, just B dot A and A dot A into A. These are the value and this is the A vector. On solving this, we will get 2 and 4. So thus the orthogonal projection of B onto A is 2 and 4. Next is projection onto a subspace or projection matrix. If we want to project a vector onto a subspace spanned by multiple vectors, we use a projection matrix. So projection onto a column space of a matrix is done by given a matrix A whose columns form a basis for a subspace. The projection of B onto the column space of A is given by P, A transpose with dot product with A and inverse for whole, then A transpose in dot product with the vector B. So here, this is our projection matrix. The example that we take is projection using a projection matrix. Let's say we have two matrices A and B with the following components, and the first step is to calculate the dot product of A transpose with A, and the result for that will be this. The next step is to calculate their inverse, and after the inverse, we will calculate the dot product of A transpose and vector B, and this will be our output. Now we have all the values that we require. The last step is to then compute PB, that is projection of B. This was our equation. Adding on to the values into it, we will get the projection as 3, 2. Then comes up applications of orthogonal projection in data science and AI. The first is PCA. So PCA projects high dimensional data onto lower dimensional subspaces that are the principal components only. This helps in dimensionality reduction while preserving maximum variance. Next is linear regression. In ordinary least square OLS regression, the predicted values are projections of data onto the column space of the design matrix. So the solution minimizes the error between observed and predicted values. The next application is in image and signal processing. Projections are used in image compression, denoising, and signal reconstruction. So Fourier transforms uses the projections to analyze frequency components. Lastly, the applications are in neural network. In deep learning, projections help in weight optimization and dimensionality reductions, and autoencoders use projections to encode information efficiently. So I will conclude with that orthogonal projections are essential for dimensionality reduction, least squares regression, and optimization. The projection formula for vectors and projection matrices for subspaces are key mathematical tools. So applications span across machine learning, AI, computer vision, and deep learning. And in the next video, we will start with another topic of foundational mathematics. See you in the next one. Till then, happy learning.